Hello, and welcome to Lesson 5 of this Introduction to Linear Algebra with Wolfram U. The topic for this lesson is matrix equations. So let's begin with a brief overview of the lesson. So let's say you have a matrix like the one shown over here. It's got 2 rows and 3 columns, and you have a vector x, a column vector, 2, 5, 1. Then in this lesson you learn how to find the product of a and x, and we're just going to call it ax, although you might want to put a dot in it if you like. Now this product will be used to define a matrix equation such as ax equal to b, where b is a vector. And what we'll show is that such a matrix equation is equivalent to, first of all, a vector equation, and secondly, a linear system. And of course, matrices are much easier to work with, so we'll always work with matrix equations wherever possible. So let's begin by trying to define the product of a matrix and a vector. So here you have a matrix capital A with n columns, a1, a2 up to an, and you have a vector with entries x1 up to xn. Then the product of a and x is defined by taking x1 times a1 and then x2 times a2 and then xn times an. So that's like multiplying a scalar by a vector in each case. Now, of course, to do that, you must make sure that the number of columns of A is equal to the number of entries in X. You need the same n over here and over there. And then, of course, you'll notice that the right-hand side over here is a linear combination of the columns of A with weights from X. So that's a linear combination. And of course, one last thing is that this matrix equation over here, Ax equal to B, is then the same as the vector equation x1 times a1 up to xn times an equal to b. Okay, so as a simple example, here is a matrix vector product. So you have a matrix over here, you have a vector over there. So what you do is you do 4 times the first column, 3 times the second column, and 7 times the third column, and you get back 3 and 6. Let's check that with actual calculations. So here is the answer from actual calculations. We have 4 times 1, 0, 3 times 2 minus 5, and 7 times negative 1, 3. Now the point is that we have a very simple but very powerful function in the Wolfram language, namely dot, which will do exactly that for you. So here's the matrix, here's the vector, and then if you do a dot x, that dot in the middle is multiplication, then you get back just the same answer. So dot is by far one of the most useful functions in linear algebra. Okay, if you look back over here, you see that the first entry 3 over here really came from doing 4 times 1 and then 3 times 2 and then 7 times negative 1. In other words, you're really doing a row times the vector. And that motivates the other approach to multiplication, which is the row vector rule. So the idea is that if you want an entry in A times X, you simply take the ith row of A and then you multiply it by the vector X. So again, here's an example. You have a matrix, you have a vector, and if you want the first entry of Ax, what you do is you take the first row of A, the 2, 3, minus 1, and then kind of lift it and place it on the first column. So you get 2 times 4, 3 times 1, and negative 1 times 3, that's 8. And for the second entry, you do 3 times 4, and then 5 times 1, and then 2 times 3, that's the other entry. And you can check that with the dot function, and you get back just the same result, 8, 23. So row vector rule is a very nice way of doing the multiplication in this case. Okay, so a few properties of these products. So if you have a matrix A, which is m by n, and you have 2 vectors u and v from Rn, then for every scalar c, for every number c, a dot u plus v is a dot u plus a dot v, just like an ordinary arithmetical algebra. and then A dot C times U is C times A dot U. And that says that the dot product kind of commutes with the addition and scalar multiplication of vectors. What that means that if you, over here you do the plus first and then the dot, and over there you do the dot first and then you do the plus, etc. So that's the meaning of commutes. You have two operations and they can be more or less interchanged. The other thing is that in future we'll say that a matrix is a linear transformations because of these very properties. Okay, so let's verify these properties in an example. So here is a matrix A and a pair of vectors u and v. So I've got A, u, and v. Let's check that if you do A dot u plus v and you do A dot u plus A dot v, you get just the same answer, and you can check that with the double equal sign, you get back true. And let's check the second property. So suppose C is 5 and you do A dot cu, you get an answer. You do C times A dot u, you get another answer, which is the same as the earlier one, and hence the two are exactly the same. So with that background on matrix products, we can now talk about the relationship between matrix equations and linear systems. So the point is that every linear system can be written as a matrix equation. Now, the matrix A over here is the coefficient matrix for the left-hand sides of the equations, whereas the vector B is the vector of constants on the right-hand side. So let's take up a particular linear system, but I first need to clear the variable x. I used it early on. Here are the equations. There are three equations and three unknowns. So the matrix A now is 2, 3, 7 from the first equation, left-hand sides, then 5, negative 1, 11 from the second equation, and 4, negative 5, 1 from the third equation. Whereas the vector B is 29, 36, negative 3 from that 29 and 36 and negative 3. So once you have A and B, you can then solve the equations using linear solve. And now that's a solution from linear solve. You can check it by plugging it back in the equations. So I use the thread function, which basically sets x to 1 and y to 2 and z to 3. And you see that you actually get back true in all the cases. So you have a relationship between a linear system and a matrix equation over here. Okay, once we understand that, then we can go a bit deeper and talk about when do solutions for a matrix equation exist. So let's say you fix A and you fix B. Then this system or this equation has a solution if and only if B is a linear combination of the columns of A. So let's check that. Here is a matrix. Here is a vector B. Right in the columns of A, A1, A2, A3. So the first column is 4, and negative 2, and 2. The second column is 5, 1, and 4. The third column is 2, 0, and 5. That's like you see over here. Now, let's try a particular linear combination. So I do 2 times the first column, 3 times the second one, and 7 times the third one. And I get back an answer, which is 37, negative 151, which is exactly the same as B. Now, question is, how to define it? I'll tell you in just a minute. But the main point over here is that this says that you actually have a solution 2, 3, 7 for the equation. And let's check the answers correct using linear solve. So you do get back 2, 3, and 7. But the point is that every time you have a solution, you really have a linear combination which lets you express B in terms of the columns of A. And on the other hand, suppose you fix your A and then you vary B. Question, what happens then? Well, so the point is that you have 3 statements over here. So first of all, suppose you know that for all B, this equation has a solution. Then that's the same thing as saying that B is a linear combination of the columns of A, or that the columns of A span the space from which B comes. So that's a relationship between A and B, but A is fixed and B is varying. So here's the matrix A, for example. Here's an arbitrary vector in 2 dimensions. Now, if I solve the system Ax equal to b using linear solve, I get back a solution. And let's check it's actually correct. So here you're trying to plug back. You do the first entry times the first column of A, the second entry times second column of A equal to B. And oh, that doesn't look right. Well, I didn't simplify far enough. So if I apply a simplify function, then I actually get back true. So the point is, it looked like we didn't get the answer over here, but in fact, just a bit of simplification gives you exactly the required result. But the main point is, in this case, we have had a solution found for all B, not just for a particular B. And of course, the statements over here simply mean that the columns of A span the plane R2 because every vector B can be written as a linear combination of the columns of A. So that brings me to the end of this lesson, and the main point is that one can compute the product of a vector and a matrix either by using linear combinations or by using row vector multiplication. And overall, the row vector multiplication is a bit easier to understand. Second, we have a very nice, powerful function called dot in the Wolfram language, which can be used to compute such matrix vector products. And of course, that's a function we'll often encounter in the course, so it'd be nice if you can get familiar with it. Now, the dot product has got nice properties, commutes with the addition and scalar multiplication of vectors. That's good to know. And finally, every linear system can be written as a matrix equation and vice versa. So, in the next lesson, we'll talk about the important concept of linear independence. But before that, do review this lesson. It's an important and basic lesson, and then be ready for the discussion of linear independence. So I stop over here. Thank you very much.